Assalamualaikum everyone. I'm Chondi Akhtar, ID 192352879, Section A, Batch 29. Today I'll discuss about identification protocols. Well, first of all, it comes in our brain that what is identification protocols? Well, identification protocol is the scheme that checks an identity of the user that sent the message on open channel. The trusted authority validates an identity of a user that aims to send messages or generates a new identity and certifies a user has denoted identity. The only aim of an identification protocol is to check that a trusted authority is satisfied of an identity of that user. Identification objectives. Identification is the process through which one ascertains the identity of another person or entity. In our lives, in our daily lives, we identify family members, friends, and co-workers by their physical properties, such as voice, face, and other characteristics. Those characteristics, called biometrics, can be used on computer networks with special hardware. Entities on a network may also identify one another using cryptographic methods. An identification scheme allows prover to identify itself to verifier in such a way that someone is listening and cannot pose as prover later. One example of an identification scheme is a zero-knowledge protocol. Zero-knowledge protocol allows a person or a server or website demonstrate they have a certain piece of information without giving it away to a person or entity they are condensing. Now, if we give example of Alice and Bob, suppose Alice knows how to solve the Rubik's Cube and wants to convince Bob she can do so without giving away the solution. They could proceed as follows. Alice gives Bob a Rubik's Cube, which he truly messed up and then gives back to Alice. Alice turns away from Bob, solves the puzzle, and hands it back to Bob. So Bob is convinced that Alice solved the puzzle without giving away the solution. This idea may be adapted to an identification protocol if each person or entity is given a puzzle and its answer is indeed each entity makes up a puzzle that only they themselves can solve. The security of the system relies on the difficulty of solving puzzle. In the case above, if say Alice was the only one person who could solve a Rubik's Cube, then this could be her puzzle. In the case of honest parties, prover and verifier. Prover is able to successfully authenticate itself to verifier. Verifier will complete the protocol having accepted prover's identity. Verifier cannot reuse an identification exchange with prover so as to successfully impersonate prover to a third party. The probability is negotiable that any party like Tom or C, you can say, distinct from prover, carrying out the protocol and playing the role of prover, can cause verifier to complete and accept prover's identity. There are 5 types of identification protocols: zero-knowledge protocols, Fiat-Simmer identification protocol, Schnorr identification protocol, Fiat-Simmer identification protocol, Julio Quiz-Quarter identification protocol. Zero-knowledge identification protocols. Some years ago, it was reported that some thieves set up a fake ATM machine in a shopping center. When a person inserted a bank card and typed in their PIN identification, the machine recorded the identification information but responded with the message that it could not accept the card. The thieves then made counterfeit bank cards and then went to original ATMs and withdrew cash using the PIN numbers they had obtained. Now we must be thinking, how can this be avoided? There are several situations where someone reveals a secret identification number or password in order to complete a transaction. Anyone who obtains this secret information can masquerade as this person. What is needed is a way to use the secret information without giving away any of this secret information that can be reused by an eavesdropper. This is where zero knowledge techniques comes in. Now, if we give example of Alice and Bob game, suppose Alice wants to prove to Bob that she knows the secret words that will open the door with the code in the cave, but she does not wish to reveal the secret to Bob. In this scenario, Alice's commitment is to go A or B. Bob goes to middle of these two paths, and there while Alice goes to and wait for a while. Alice goes to see A or B. Bob then goes to B and shouts to Alice to appear from either the right side or the left side of the tunnel. If Alice does not know the secret of words Open Sesame, there is only a 50% chance that she will come out of the side of the tunnel requested by the Bob. Bob can repeat this challenge as many times as he desires until he is certain that Alice knows the secret words. In such a round, of course, Alice randomly chooses which side is the tunnel she will go down, and Bob randomly chooses which side he will request. Therefore, if Alice comes out the correct side of the tunnel for each of 10 consecutive repetitions, say there is only one chance in to the power 10, which means 1024, that Alice doesn't know how to go through the door. No matter how many times the proof repeats, Bob will never know and learn the secret words. Suppose Oscar is watching the proceeding on a video monitor set up in the middle. He will not be able to use anything to see to convince Bob or anyone else that he too go through the door. Moreover, he might not even be convinced that Alice go through the door. After all, Alice and Bob could have planned the sequence of rights and lefts in advance. By this reasoning, there is no useful information that Bob obtains that can be transmitted to anyone. There is never a proof in the strict mathematical sense that Alice goes through the door. But there is a overwhelming evidence that she can obtain through a series of challenges and responses. This is, in sense, the nature of zero knowledge proofs. Mathematics of zero knowledge protocols. Euler's Boolean function is written as phi n, where phi n is the number of positive integers. The integers a and b are relatively prime if they have no prime factors in common. That is, if their only common factor is 1. This is equivalent to saying that a and b are relatively prime if GCD a comma b equal 1, where GCD AB stands for greatest common divisor of a and b. For example, phi 21 equal 12, where the 12 integers 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, 20. It follows from the above that for a prime number p comma phi p equal p minus 1. Now suppose that we have two prime numbers p and q, and for n equal p into q. So phi p q equal p minus 1 and q minus 1. Example 21 equal 3 and 7. So phi 21 equal 3 minus 1 following these rules, and 7 minus 1 equal 12, and the 12 integers are listed above. Fiat-Simmer identification protocols. The objective is for Alice to identify herself by proving knowledge of a secret S to any identifier, such as Bob or a trusted center called Tom, without revealing any information about S not known or computable by Bob or Tom prior to execution of the protocol. The security of the method relies on the difficulty of extracting square roots. Modular large composite integers n of unknown factorization, which is equivalent to factoring n. The protocol involves the following steps. One-time step up, setup, protocol messages, protocol actions. One-time setup. A trusted authority, call it Tom, selects two large prime numbers p and q, calculates n equal pq, publishes n, and keeps the prime numbers secret. L is a user of the center. Select a number s in the range 1 to n minus 1 that is relatively prime to n, calculates v equal s square mod n. Registers V as her public key with Tom, keeps her password S secret, and carries both S and V with her. Alice and Bob agreed on a maximum number of routes T of the identification protocol that will be carried out at login. Protocol messages. Each of T rounds has 3 messages as follows: Alice to Bob, Bob to Alice, Alice to Bob. Protocol actions. The following steps are iterated T times sequentially and independently, both except the proof if all T rounds succeed. Alice first generate a random number R in the range 1 to n minus 1. This is called her commitment. She calculates witness and send X to Bob. Over receiving X, Bob selects a bit E, either 0 or 1, at randomly called a challenges, and sent E to Alice. On receiving E, Alice calculates Y equal R into S to the power E mod n. If equals 0, then Y equal R, and if equal 1, then Y equal R into S mod n. Y is the called the response. She needs Y to Bob. Receiving Y, Bob calculates Z equal Y square mod n and Z prime equal X into V to the power E mod n. If Z not equal Z prime, he refuses the login from Alice. If Z equals Z prime, he accepts the round of protocols. The following congruence shows that Alice will be able to prove their identity to Bob. Suppose X equal V to the power E equivalent R square into V to the power E mod n. Equivalent R square is to the power 2E mod n. Equivalent R into S to the power E and R into S to the power E mod n. As we know, Y equal R into S to the power E mod n equal Y. That's why Y square mod n. So Bob will accept Alice's proof of the identity. Converting identification to signature schemes. and identification scheme involving a witness challenge response sequences can be converted to a signature scheme as follows. Replace the random challenge E of the claimed or prover by the one-way public hash function H of the witness X and the message M to be signed. This, in fact, converts an interactive identification scheme to a non-interactive signature scheme. The challenge must be difficult increased, be increased to avoid offline attacks on the hash function. Overview of connection. The identification protocol provides a means to determine the identity of a user of a particular TCP connection. Given a TCP port number pair, it returns a character string which identifies the owner of that connection on the server system. This is a connection-based application on TCP. A server listens for TCP connection on TCP port 113 decimal. Once a connection is established, the server reads a line of data which specifies the connection of interest. If it exists, the system dependent, the user identifier of the connection of interest is sent as the reply. The server may then either shut down of the connection or it may continue to read or respond to multiple queries. The server should close the connection down after a configurable amount of time with no queries. The client may close the connection down at any time. However, to allow her network delays, the client should wait at least 30 seconds for a query before abandoning the query and closing the connection. Summary. Identification protocols that can prove an entity's identity without the need for the entity to reveal any information about itself are to be welcomed. As a result, we anticipate that identification protocols will grow in importance as we seek new ways to negotiate the conflicting needs of privacy on the one hand and proving our identity on the other. Those are references. Thank you, everyone.